Alright guys, good afternoon. In this video today we will discuss how to find the area under the curve by the use of limits. Okay, so the first thing we need to talk about before we can actually get to the task of finding the area under the curve with the use of limits is we need to make sure that we review that you are familiar with the idea of sigma notation. So the idea of series. Okay, so hopefully you remember this from your time in maybe geometry and pre-calculus. So a series, by the way, this is called sigma. This is the Greek letter sigma, which means summation, at least in mathematics. Cool. So in order for you to have a series, you have to have a sequence. So I'm going to have a sequence right here, some type of sequence. Okay, a series has to have an index of summation. For in this case, I'm using the letter I, since this sequence is using the letter I. We're going to start it at 1, okay, and then we're going to end at n. So remember how this works for a series is you plug in the value starting at whatever you have here. So this would be ace of 1 plus ace of 2 plus ace of 3, and you keep going all the way until you reach this number, which in this case would be ace of n. Okay, so in this video, we're not going to focus so much on the introduction of this and what they are. Hopefully, at this point, you should have been familiar with them. So let's just practice to make sure that you at least know how they work. So let's say, for example, I give you a series such that you have an index starting at 1 and ending at 5. And it's literally just a, I don't know, I squared plus 1. Well, the way that this works is we're going to plug in 1. So that's going to be I squared plus 1. So that's going to be 1 squared plus 1, which is 2. Plus then 2 squared, that will be 4, plus 1 is 5, plus then you plug in 3, that's 9, and it's 10. You plug in 4, that's 16, that will be 17, and then you're going to stop at 5, so that's 25, that's 26. So let's pause. Without the symbol, this would be a sequence, and this would be the terms of the sequence. Because we have this symbol, now we're going to go ahead and add them all. So what do we got? 5 plus 2 is 7, that's 17. 17 and 17 would be 34. 34 and 6 is 40, so I'll be a total of 60. So that means that the series, or the summation of the 5 terms of this sequence, would equal to 60. Okay? So hopefully this brings back a little bit some hopefully good memories from your pre-cal days. Okay? Alright, now, why am I bringing this up? We're going to have to use the idea of summations to help us out find the area under the curve. Okay, but before we can get there, I need to introduce you to a couple of properties and some summation formulas. So first we'll talk about some properties of summations. And these properties can become very helpful for you, especially when we're doing the area under the curve. Okay, the first property is, let's say that we have a series in which the index is 1 to n, and you have some kind of constant in front of your sequence. What that means is that after you plug in every number, you're just going to multiply by k every single number. So what you can do is, instead of just doing that for every single number, you can pull out that number, so that constant. You can do your summations, and then when you're done, you can multiply by k. Cool? So in other words, you can pull out the constant from a summation. Okay? The other property that could be helpful for us is that if you have a series in which you have the addition or subtraction of different sequences, it could be helpful to break that up into separate series, so you can separate them. So this would be like the summation property of series. Okay, very helpful for us. Okay, so those are the 2 properties that are going to help us out, just really reduce our work. Okay, now we also have some summation formulas. By the way, these are properties and formulas that you will need to memorize. I will not be providing this for you. Okay, now the following formulas we are not going to prove. Okay, if you are interested on where they come from, I would suggest a really quick Google search. I'm 100% sure you'll find a good video that would allow you to show you where these formulas come from. So for the moment, I'm just going to go ahead and provide them for you. Okay. So the first series that we're going to talk about, or the first summation formula, has to do with a series with an index beginning at 1. And this is very important. All of these formulas only work if the index starts at 1. So it's 1 to whatever, to n, whatever value that is. It could be 5, it could be 100, it could be 1,000, it doesn't matter. So it's 1 to the n of a constant. That is going to be equal to the constant multiplied by n, whatever this is. Cool? The second one we need to talk about, once again, is if the index begins at 1 and it goes to n of I. Cool? That is going to be equal to n times n plus 1 divided by 2. The third one we will talk about in this class would have to be with a series whose index begins at 1 and it ends in n of I squared. That will be equal to n times n plus 1 times 2n plus 1. Times 2n plus 1 divided by 6. And then the last one that you will need for this class would be the series whose index begins at 1 and it ends at n of I to the third power, and that's going to be equal to n squared times n plus 1 squared divided by 4. Now at this point you may be a little bit like wondering, like, what is going on? What are we doing with all this? Give me just a second. We're going to do some examples just using this, and then finally, once we do a couple examples with this, we're going to go ahead and move on to the idea of area under the curve. Okay, so here's our first example. So you've got a series here, and you are being asked to evaluate the series at when n is 10, 100, and 1000. So simply what that means is we would plug in a 10 here, and then we would plug in a 10 here. And when it's 10, it's actually not that bad. We can plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then add up all those terms. Cool? Not terrible. But if it's 100, then we have to do this 100 times. And if it's 1,000, we have to do this 1,000 times. So rather than doing that and plugging in, we're going to go ahead and use this idea of using the summation formulas as well as those properties to help us out. So first of all, I want you to observe the following. N would represent whatever number we have here. So if I plug in n here, then I would have to plug in, like for example, if I plug in 10 here, I would also have to plug in 10 here. Which that means then is n squared is just going to be a constant. Right? So depending on whatever this is. So what I'm going to do is I'm going to use the properties real quick. And I'm going to pull out this 1 over n squared. Because that is just a constant. So I still have an index starting from 1 and going to n. And then I'm going to have I plus 1. So that's the first property I use. I use the constant property. Now I'm going to use the second property, which is because I have an addition here, I can split this up into two separate series. So I'm going to go ahead and use a bracket here. So I've got the first series starting from 1 to n of I, plus the second series starting from 1 to n of 1. Okay, are we okay thus far? Alright, so next, I'm going to see if I can use some summation formulas. Well, notice that this index starts at 1, it goes to n, and it's I. So there is a summation formula for that. And I'm going to go ahead and replace it with that summation formula. So the summation formula for that would be n times n plus 1 divided by 2. And I also notice that this is just a constant. It's just 1. So there is a summation formula for that. And the summation formula for that is just the constant times n. So in this case, 1 times n is n. And look at the beauty or the advantage of this. I no longer have a series. I have completely replaced that with formulas, and everything is in terms of n. So what I'm going to do is I'm going to go ahead and clean this up, and then I'm going to be able to plug in 10, 100, and 1000 to figure out the correct summations for each one of these. Alright, so let's go ahead and start the task of cleaning this up. So I'm going to go ahead and distribute this out. So this would be n times n plus 1 divided by 2n squared plus n over n squared. So this very first one I'm going to be able to cancel out an n. So I'm going to be left with n plus 1 divided by 2n. And the second one would just be 1 over n. And if you really wanted to, we can get a common denominator and go about it this way. Go ahead and add them. So I'm going to multiply by 2. So I'm going to multiply that by 2. So I'm going to have a common denominator, which is going to be 2n. And then this would become n plus 3. So here's the beauty of this. Now you've got this summation here. We started with this series in which the index was 1 to n of I plus 1 over n squared. And we know now, by the use of summation formulas, that that is equal to n plus 3 over 2n. So now you can actually figure out the 3 summations that you were asked. So we can do the summation from 1 to 10 of I plus 1 over 10 squared. That is going to be equal to 10 plus 3 divided by 2 times 10, which is 13 over 20. So that's our first summation. So look how easy that was. We didn't have to find 10 terms and add them. Now we're going to do the same thing for a summation from 1 to 100. So we got I plus 1 over 100 squared is equal to 100 plus 3 over 2 times 100. So that's going to be 103 over 200. And then we've got our third series, which was 1 to 1,000 of I plus 1 over 1,000 squared. That is going to be equal to 1,000 plus 3 over 2 times 1,000. So that's going to be equal to 1,003 divided by 2,000. First, I want to make an observation that hopefully you can see. Do you notice that as this number increases, the summation begins to approach a certain value? So this is 13 over 20. Okay, that's not that bad. That's a little bit more than half. 103 over 200, that is a little bit more than half, like little bit. And then we have 1,003 over 2,000. It's getting closer and closer. It seems to be 1/2. So here's my question. What if I wanted to know if this was infinity? So if I wanted to know what is the summation from 1 to infinity of I plus 1 over n squared. Well, we already know that that is equal to n plus 3 over 2 to the n. We can't plug in infinity, but we can use calculus to help us out, which in this case is, what if I take the limit as n approaches infinity of the summation, which in this case is n plus 3 over 2n. Well, by the rules of limits, because these are the same power, we can use the rules of asymptotes, horizontal asymptotes, and that would equal to 1/2. So that means that if I were to go to infinity, we're going to get the exact value of 1/2, or we're going to approach 1/2. Okay? Why am I introducing this? Because this is what we're going to do with area. Okay? We want to find area under the curve by the use of limits. So the way we're going to be able to do that, guys, is last video that you watched, you were able to find area by approximation with the use of rectangles. And the best way to get a better area is to increase the number of rectangles. So if we increase the number of rectangles to eventually approach infinity, we're going to have to use the idea of limits so that we can figure out exactly the area. So that's what we're going to go ahead and do. Okay. Now that you feel comfortable, so hopefully you feel comfortable with the idea of sigma, we're going to tie that into the idea of area under the curve. Okay. So here's the example that we did on the previous video where I gave you this function. So we got 5 minus x squared from 0 to 2. But in the previous video, I asked you to find the area with an approximation using 4 rectangles of equal width, right? So what you ended up doing was, okay, you're like, okay, so if it's 4 rectangles, you took the distance from here to here, which is 2, you divided that by 4, and then you got 1/2, and then you made your rectangles, and then you find the area of each rectangle, okay? But if we're looking for the exact area, that means we can't really use an approximation. We're going to be able to use rectangles, but not just one. We need an infinite amount of rectangles in order to do this. So let's kind of come up with a strategy. We're still going to use rectangles. So we know that the area of a rectangle is equal to width multiplied by height. Okay, so let's talk this through. The width for us, when we had 4 rectangles, let's talk this through. Let's just pretend we had 4 rectangles. You guys went ahead and did this, right? You drew a line there, and then let's say we use right endpoints. So you came up with 4 rectangles with right endpoints that look like this. Cool? Well, let's talk this through. What was the width? Well, the width was this part right here, right? So let's think this through. How do you find that width? Well, you took the distance from here to here, and you divided it by how many rectangles, right? So if we want an n amount of rectangles, what we're going to have to figure out then is, what is the distance between these two? Well, that's just 2. And we're going to have to divide it by the number of rectangles that we want, which in this case is n rectangles. Okay? So that's going to be our width. Now, how do I figure out the height of one of those rectangles? Well, let's think this through. Let's go back once again to this idea of the 4 rectangles. So once you figure out your widths, you're like, okay, well, this first height right here, I can figure out what this height is by doing figuring out what this point is. So I would have to do f of this very first value, so which was f of 1/2, right? You're like, okay, if I can take f of 1/2, I can figure that out. And then f of 1, and then f of 3/2, and then f of 2. So it looks like as long as you know what your right endpoint is, you're going to be able to know what to evaluate. We'll think this through. For the 4 rectangles, you took 2 and divided by 4, which gave you the 1/2. But I'm going to use the unsimplified version here, so 2 to the 4. So it was 2/4, right, and then 4/4, and then 6/4, and then 8/4. So I need to come up with an expression that gives me those values. So like if you had 2/4, 4/4, 6/4, and then 8/4. Well, by the look of it, okay, if I can come up with an expression, I always have a 4 there, and these are multiples of 2, right? So I can say, okay, this is technically just 2/4 times I. If I multiply by 1, I get the first one. If I multiply by 2, I get the second one. If I multiply by 3, I get the third one. By 4, I get the fourth. So I can come up with an expression that's basically 2/4 I, or 1/2 I. Now, if you notice, this matches exactly what the width is. So if I want to figure out the height, what I'm going to have to do is take f and evaluate it, in this case, at 2/n I. Okay. So now this gives you the area of one rectangle, but we want many rectangles, and we want to add a lot of those rectangles. So what that means, let me go ahead and scratch all this out, is that we need to introduce the idea of sigma. We want the addition of the summation of 1 to n of this expression here. Okay, so at this point we're like, okay, let's talk a few things when I look at this. N is just a constant, so 2 to the n is a constant, so I'm going to go ahead and be able to pull out a 2 to the n. Now I'm left with this idea of f of 2/ni. So what does that mean? Well, think about it. Anytime you have f of something in the parentheses, means that you have to introduce this into the function. Now remember, our function for this problem is f of x is equal to 5 minus x squared. So what that means is that we need to plug this into x squared. So then this will become 2/n of the summation from 1 to n of 5 minus 2/ni squared. Okay, all I did was take the 2/ni and introduce it into the function. So I'm just going to clean up this a little bit. So we've got a summation from 1 to n of 5 minus, if I square this, this will become minus 4/n squared I squared. Are we okay with that? So now what I'm going to do is I'm going to use my properties of summations and split the summations into 2, take out some constants, and then try to attack it with the summation formulas. Okay, so I'm going to go on this route. So I got 2/n on the outside. I'm going to have some brackets. I'm going to have the first summation start at 1 and go to n, and it's just going to be of the constant 5. Minus, now 4/n squared once again is going to be a constant, so I'm going to pull out a 4/n squared, and then I'm going to have a summation from 1 to n of I squared. Okay, so now it's time to go to our summation formulas. We have a summation formula for a constant, and remember the constant is simply just the constant times n. So this very first summation gets replaced with 5 times n. Now I have this 4/n squared on this side, and I have an I squared. And the summation for I squared will get replaced by the summation formula of n. So I'm going to go ahead and put parentheses, n times n plus 1 times 2n plus 1, all divided by 6. So I have successfully replaced all of my series with just summation formulas, which means they're all in terms of n. And if I want to find the exact area, all I have to do is take the limit of this as n goes to infinity. So this is what I'm going to go ahead and write. I'm going to take the limit as n approaches infinity, and I'm going to clean this up. So I'm going to multiply things in. So if I do 2n times 5, 2/n times 5n, that's going to give me 10n divided by n. Cool. And if I multiply this by that one, it's going to give me minus 8/n cubed. and then I'm going to multiply this out here, see what happens here. So we've got, no matter what, I have a 6 here. So this gives me what? N squared plus n multiplied by 2n plus 1. So in other words, I got a little bit of algebra to do before I can actually take the limit. I do recommend that you do the algebra first, personally. Okay, so now we're going to take the limit as n approaches infinity. We're going to let this n's cancel out, so it just leaves you with 10 minus 8 over n to the third multiplied by, okay, let's see what we got going on here. We got a 6 here, and that will give us a 2n cubed plus n squared plus 2n squared plus n. Okay, so good. So far, so good. I'm going to go ahead and carry this page, sorry, so you guys can see and I can continue. So I'm going to go ahead and continue, and I think this would be my last step. I think I should be able to solve it from here. So now I'm going to have the limit as n approaches infinity of. The 10 is going to remain by itself. Okay, so now I'm going to multiply this in. So I'm going to have minus 8 times 2 gives you 16. That's going to give you 16n cubed. And then we have n squared and not 2 others n squared, so that's going to give us 3n squared times 8, so that's going to give us 24, so a negative 24. Well, actually, I'm going to leave the negative here, so I'm just going to multiply that in. So plus 24n squared. And then lastly, we have 8 times n, that's just 8n, all over 6n cubed. So I've got to multiply that n cubed to the inside. Okay? All right, let's make sure I didn't make any mistakes, any silly mistakes. So 8 times 2 is 16. We got 3. 8 times 3 is 24. Okay, so we're good. So now I think I can go ahead and take the limit here. Okay? Notice the limit of a constant is just the constant itself, so that's just going to be 10 minus. I have a rational function here. I'm going to compare the exponents. So this is n to the third, and this is also n to the third, which means that I can divide the coefficients. So 16 divided by 6, that's going to give us 8 over 3. So what that means is that if I take 10 and I subtract 8 thirds, so first of all, that 10 will be 30 over 3. So 30 minus 8 would have to be 22 over 3. So what this means is that, therefore, the total area under the curve of 5 minus x squared from 0 to 2 is 22 over 3. And that would be our final answer. Okay? All right. Hopefully you feel like this wasn't that terrible. It does take a little time. It can be a little time consuming. It can be a little daunting too. But the key for you to do this, first of all, is you've got to know your summation formulas. And two, honestly, this is where I see students struggle a lot. If I go back to this very first part, is can you come up with this expression? Okay, how do you figure out the area with an n number of rectangles? Okay, this is where students struggle the most. Okay, now notice the example that we did was using the right hand side. So coming up with this expression was relatively simple. The other thing I want to bring up is in order for you to use those summation formulas, your index has to begin at 1. So for example, let's say we want to do the same problem, but instead of using the right endpoints, we want to use the endpoints. Well, a lot of students try to do, well, let me just plug in a 0 here so that I can start at the left. But if you plug in a 0 there, that means that your summation has to start with 1. So the way to fix that, so let's say we want to do a left endpoint. So by the way, this was right endpoints. If we want to do a left endpoint, we have to get a little creative. And what I mean by that is we still want to use the idea that it's every 2 over n, but we want to start with 1 on our index, right? So, but because of the left endpoint, at least for this one, the first value is 0. So the way to do that is, okay, we're still going to have the same width to find the area, right? But instead of f of 2n over I, we're going to have to do 2n times I minus 1. Let me explain to you why, or hopefully you can see why, okay? Because our index has to be 1, the first value that I enter would be 1. 1 minus 1 is 0, which then matches what I want, and then the rest of this should work out, okay? So to do the left endpoints, honestly, first of all, to do the right endpoints, honestly, what you can do is every time you find the width, it's going to be times I. Cool? And to do the left endpoint, it's going to be times I minus 1. Now, the advantage that you have on the problem that I'm giving you in this video is that I'm going from 0 to 2, okay? If you're not going from 0 to 2, like for example, let's say that it was from 1 to 2, so that means we would only be interested on this part right here, then you have to get a little creative, because instead of starting at 0, you're starting at 1, right? So if you want to do the right endpoints, the very first value would have to be 1.5, right? In this just using, in this case, just 2 rectangles, right? So how are you going to do that? Is you have to come up with a different expression that allows you to start there. So what you would do in this case, I would say, is once you have this expression, you would have to do plus whatever value you're starting at, plus 1. So let's think that through, right? So if our very first value we want to do, and it's a right endpoint, that would be the 3.5 right here. If I plug in 1, that's just gonna give me 1 over 2 over, by the way, we're using 2 rectangles, so 2 over 2 would be 1, right? I mean, sorry, 2 over, let's say we are using 2 rectangles, and from here to here is 1. 1 divided by 2 is 1/2. So this would be 1/2, okay? Times 1 is 1/2, right? And if you do plus 1, that gives you the 1.5, which is what we want, right? Let's say we were using 3 rectangles. So 3 rectangles will be, the length right here will be 1. So 1 divided by 3 is 1/3, right? So it would be 1/3 I, right? And then if we're starting at 1, it's plus 1, so that gives you 4/3, which is where we want to start. So in other words, if it's another number other than 0, once you come up with the expression, all you have to do is plus wherever value you're starting. If it's a negative, then obviously it's going to be a minus, okay? Hopefully I didn't confuse you too much about that. I just don't want to make this video super long where we do another problem in which we have to do the exact same thing. And in my opinion, I think you guys are capable of doing such thing and coming up with the expression on your own. Okay, so for homework, there's going to be a few of them where I recommend personally, okay, you use right endpoints. If you're not being told to use left endpoints, then there's no reason to do it. Here's the reason why there's no reason to do it, guys. Whether you use right endpoints or left endpoints, you're going to have to take the limit to infinity. And at the end of the day, you're going to get the same answer. The left endpoints require you to think a little bit more because you're starting at the left, so your expressions are going to be a little bit bigger. So what that means is if you plug this into the original function, it's just going to bring in more terms. That's all it's going to do. Okay. So once again, my recommendation is to use right endpoints unless you're being asked to do another type. Unless you're being asked to do the left endpoints. Okay. Other than that, guys, I mean, that's all I want to do for this video. It's already almost at 30 minutes, so I don't want to make it any longer. So make sure that you do your homework, you practice this. Your quiz will have problems in which I will be asking you to find the area by the use of limits. Okay? Other than that, I'll see you next time. Take care.